Okay, so let's get around this business about when is a columnar structure a vortex and when is it a wave packet. We go back to G.I. Taylor's original experiment back in 1921. So we've got a rotating tank, and we put a slug or some object at the bottom, and it slowly moves from left to right. And you get, of course, a so-called Taylor column. That's to say, as this slug moves from left to right, all of the fluid contained within this cylinder which circumscribes the object, all of this fluid gets dragged across the tank in tandem with the object. It's called a Taylor column. In other words, the fluid doesn't do what you'd expect. The fluid doesn't rise up and over the object. You get a purely two-dimensional motion with this column going across and the fluid outside the column going around the column in a two-dimensional fashion. It's a lovely experiment to do. Undergraduates love it. You can tell what's happening by just, you drop dye in at point A, you look down from above and you see the dye at point A just drift across the tank centered above the object. Or you put dye in at point B and you look down from above, and as the object passes below the dye, you see the dye stream separating to make room for the cylinder. If you do this in the lab, and you don't look too carefully, this thing looks awful like a vortex. So it's not. It's a wave packet. And the clue is you have to ask, well, I'll give you what we tell undergraduates, at least in Cambridge. I'm sure you don't say this in Marseille. So when we teach this to undergraduates, we lie. We say the explanation for this is the following. We say this is moving slowly, so it's quasi-steady. Quasi is the most dangerous word in physics, I think. It's quasi-steady. So the force balance, there's no inertia, so the force balance is pressure gradient, balance is Coriolis. I take the curl to kill the pressure gradient, and I just end up with omega dot grad u is 0, or if z is in the omega direction, du dz is 0, so the flow is two-dimensional, and that's why the fluid does this, is to maintain two-dimensionality. In geophysicists would call that geostrophy. But I say that's at best a rationalization of what's going on and not an explanation, and the answer is, the reason I say that is that you have to ask, how does the fluid at point A, how is it smart enough to know that when my object moves 1 centimeter, it moves 1 centimeter? How does the information get from here to here? And the answer is these inertial waves. That what's happening, it's not static, this is wrong. So as this object moves from the base of the tank, it's acting like a radio antenna, and it's shooting off inertial waves, because I'm in a wave-bearing system. I move my object slowly, so these are low-frequency inertial waves, and it so happens that low-frequency inertial waves want to propagate up or down the rotation axis. Higher frequency ones can go obliquely, but we've got low frequency here. So this, as it moves, is producing inertial waves that shoot up, hit the surface, come back down, and those inertial waves are carrying the information that the object's moving at a certain speed. If you don't believe me, there's a nice thing you can do in the laboratory, which is just move the object slightly faster. Still slowly, so it's low frequency, but just a little bit faster. And what you find is, when you move a little bit faster, the column bends over, and it bends over at an angle which is exactly what you get if you take the superposition of the velocity difference between the object and the fluid in the horizontal direction and the group velocity of inertial wave packets in the z direction, and you get exactly the right angle. And that tells you that without any doubt, this is not a vortex. This is essentially wave packets, or waves streaming off the object. So the hidden message here is, when you do a simulation in a rotating fluid and you think you're looking at a vortex, be careful. You might be looking at wave packets. Wave packets behave quite differently from vortices in a conventional sense.